All right, this is the second video of, this would be 9.02 of our rotational motion chapter, and we're doing the graphs of rotational motion. And it's going to be kind of a short video because it's actually not very difficult. The graphs for rotational motion match the graphs that we have for linear motion. So if you remember, if I have xt, and I have a parabolic here, that's going to give me a VT that looks like this. And that's going to give me an AT that looks like this. Let me do my line in a separate color here. Give myself a little contrast. And we said that if we were in calculus, we would do the first derivative to go from our xt to our vt. We would do our second derivative to get our AT. So the slope of an xt graph gives us our velocity. Slope of our xt gives us our velocity. So in this case, because it's not a straight line, we would have to do instantaneous velocity. We would have to find the line tangent to the point. The slope of a VT graph gives us acceleration. So we see that we can go in that derivative, we're finding the slope, and the slope of xt is velocity, the slope of vt is acceleration. Now remember, we can go backwards as well. So if I find the area under the curve, so this area, the area under the curve is our total displacement. So I can go backwards by using integrals. And again, we learned that back at the beginning of the year. One of the things you want to watch out for, again, so if you look at this, you're looking at the slope, that's going to give you your velocity. When you're looking at velocity here, one of the toe trippers is that you want to look at this line, and the velocity is now over here. This is acceleration. So make sure you know what kind of graph you're looking at. So the only thing that we're going to do different is basically we're going to change this to angular displacement, which is theta. We're going to change this to angular velocity, which is omega, and we're going to change this to angular acceleration, which is alpha. All right, I have some AP practice problems here. They're a little tough to read, but hopefully if you want to, you can pause the video and copy it down or just walk through it with me. So I have angular speed. So I have an omega here versus time. An object rotates with an angular speed that varies with time as shown in the graph. How can the graph be used to determine the magnitude of the angular acceleration of the object? Subtract the greatest value of the angular speed from the smallest value of the angular speed because alpha equals the change in omega. I need to check something. Okay, making sure I wasn't on mute. B, determine the slope of the line from 0 to 2 because the slope best represents the change in angular velocity over the change in time. C, determine the area bounded by the line from 0 to 2. Or D, the angular acceleration cannot be determined without knowing the rotational inertia of the object. Well, what we just said was, we know the slope of the line, that's going to give us our angular acceleration. So the slope is equal to here. So we would have, this is going to be equal to theta. Here it's going to be equal to omega. So the answer here has to be B, finding the area, that's going to give us our total displacement. Okay, let's move on to the next problem. All right, take a second if you want to pause the video, see if you can get the answer here. Okay, a graph of the angular velocity omega as a function of time t shown for an object that rotates about an axis. 3 time intervals, 1 to 3, are shown. Which of the following correctly compares the angular displacement theta of the object during each time interval? So they have here theta of 1 is equal to theta of 3 and is greater than theta of 2. Theta of 2 is greater than 1 and 3, which are equal. Theta of 3 is greater than 2 is greater than 1, or theta 1 is greater than 2, it's greater than 3. If you haven't paused the video yet, do so. See if you can figure this out. All right, remember, theta is the area under a curve. So if I break these down into sections, I've got those two sections, which are the same, and then I have this section. This is going to have a greater area than these two. So what I can say is that section 2 is greater than 1 and 3, which are equal to each other, which is B. All right, let's do one more. An axle passes through a pulley. Each end of the axle has a string that is tied to a support. A third string is looped many times around the edge of the pulley, and the free end attached to a block of mass MB, which is held at rest. When the block is released, the block falls downward. Consider the clockwise to be positive direction of rotation. Frictional effects it should be from the axle are negligible, and the string wrapped around the disc never fully unwinds. The rotational inertia of the pulley is 1/2 mr squared. That should be a squared about its center of mass. Which of the following graphs, if any, shows the angular velocity of the pulley as a function of time t after the block is released from rest? I'm going to see if I can focus this a little more. It's about as good as it's going to get. All right, pause the video, see if you can answer this. All right, let's keep in mind that we are looking at angular velocity, so we have omega here. So let's look at these. We know that our acceleration, so we're in free fall because we're ignoring friction, so our acceleration has to be 9.81 meters per second squared down. So right away, we know that this one's out. The slope of this is 0, and we know that the slope of an angular velocity time graph is equal to our acceleration. So this is not going to work. There's a 0 acceleration there. Here we have parabolic. Well, this isn't going to work because I'm not going to have a constant. So when I graph this, my AT graph would look like this, which isn't the case. We know that it has to have a value. The AT graph has to look like that. So this is out. So the question is, which one of these two is it? Is it the one where the slope is positive or the one where the slope is negative? Well, the trick here is they say clockwise is the positive direction of rotation. And that's the direction that the block is going. So the slope here has to be positive. This one won't work because of the clockwise direction is positive. Okay, so again, this was a shorter video, but it's really review. When you look at something that's rotational, you don't have to worry about whether or not, you don't have to throw in anything new because it operates the same way as it did when it was linear. All right, in the next video, we're going to be doing angular kinematics. All right, until then, thanks for watching.